Okay, we'll talk about the chain rule. Um, it's all about compositions. That's what the chain rule involves, compositions. I try to give you a little example here, a concrete example starting here. If you, let's say you're packing baskets for selling, and the baskets have to contain numbers of plates, spoons, and things like that. Each basket might have to have 4 plates. Each plate needs 2 spoons to go with it. So the question is, how many spoons do you have to make for every basket? And you can probably tell that you're going to just have to look and say, well, for every plate, I need 2 spoons. If I have 4 plates, then I'm going to need 4 times 2 spoons for every 1 basket, because each basket contains 4 plates. So intuition kind of tells you that just multiply the 2 by 4. Now the 2 and the 4 are actually rates. It says 1 basket for every 4 plates. So you can say 4 plates per basket. That's a rate. 2 spoons per plate. So these are rates. And in order to get the rate of spoons per basket, you have to multiply these other 2 rates, the number of spoons per plate by the number of plates per basket. And that'll give you that number. So in calculus terms, using our terminology, our vocabulary that we have here and our symbols, things might look like this. The rate of spoons per plate, ds dp, spoons per plate is 2. The rate of plates per basket, dp db is 4. So the rate of spoons per basket, ds db, is the product of these 2 rates, ds dp and dp db. So you get 8 spoons per basket. Anyway, and here's another way to view it in terms of our composition notation. S is f of p, p is g of b, so S must be f of g of b. And when you find the derivative, you will be multiplying the rates, okay, like this. So when you form that composition, you'll be multiplying by the rates. Now this takes a proof to get this proof, to what's the word, rigorously prove that this is something we can use all the time. We require a proof, and we're not going to do the proof on this one. It's in the textbook. It's a little advanced, but we won't waste time on the proof. We will waste time on executing the proof, or the theorem that comes from the proof. So this is called the chain rule. Some reason they call it the chain rule. I think it's because of the compositions, the way they're nested inside of each other. And then you have this product of the rates. So now here's in symbols what we would use for the chain. Officially, dy dx is dy du times du dx, assuming that y is a function of u and u is a function of x. Okay, so that's what this means. U is a function of x, and this is y is a function of u. So indirectly, y is a function of x also. So we can differentiate it with respect to x. And this is how we do it. We treat this as a function itself with u as a variable, and then we multiply by the derivative of this function, g of x, with x as a variable. So here's in symbols also. All right, let's take an example and see how this works. And here I've listed the general power rule in general. We'll talk about that in a minute. Okay, so here we have compositions here. So we have 2 functions essentially here. We have a sine function, and we have this function 3x. So the composition, the sine of 3x. So you have to view this, one of the functions as the outside, so to speak. The outside in this case is the sine function. And then what happened is it was composed with this 3x. So it became sine of 3x. Now the derivative is you take a sine function and you just say, well, derivative of a sine is a cosine. Like that. And leave the 3x there. Okay, now if it were just an x, we'd be done. But it's a 3x. So now I have to take and multiply it now by the derivative of that 3x with respect to x. So this first part here is the dy du. This part is the du dx. That goes over here. So in other words, the y function is the sine, and you can consider it as the sine of u being 3x. So the derivative of the sine of u is just cosine of u. But since it is not just, u is not the variable, the independent variable, x is the independent, you need another derivative. So derivative of the 3x now finally is a 3. And that's our answer. We'll write it as 3 cosine 3x like that. Okay, so you got to do a few of them before you get used to it. Here we have a composition. This is the inside. This is the u, and it's being raised up to the 8th power. So when we go to take the derivative, we need the derivative of this function with respect to u, which is an 8u to the 7th, lower the power, times the derivative of the u. Well, the u is x minus 5. Du dx is just a 1. So I just need a 1 there. Okay, now I don't want u in my answer here. I have to think of that as 8 times x minus 5 to the 7th power. Okay, now I temporarily put the u in there just so you can see that I'm treating that as a single variable u, and when I differentiate it, I'm just looking at it like this, u to the 8th, and I bring the 8 down and lower to 7. Now, I left out the x minus 5 just temporarily, and maybe for convenience, maybe so you can visualize it better, but we need that x minus 5 in the final answer. So I put it back in either way. And most times, I will, in the future, I'm going to just start to leave it there and drag it throughout the problem. I won't replace it. But I want you to start thinking in terms of these compositions and seeing the compositions. Okay, let's continue. We got 2 more of these to do. Okay, now you got a function here. It's basically a squaring function. You can view it as a squaring function. And inside the squaring function is a sine function. Inside the sine function is another function, the 4x. So we've got like a triple nested composition here. Okay, a nested composition. So we'll need the chain rule. G prime of x. First you look at the squaring function. If you just had a function like this, u to the 2nd, then you would differentiate it as a 2. And here, notice my u is a sine of 4x. Okay, so I would need the sine of 4x here. Okay, and then lower it to 1 power, like that. So I brought down the 2, lower it to a 1. That's kind of treating it like a power function. Now, since it wasn't just an x, but a sine of 4x, I need to multiply by the derivative of the sine of 4x. Well, that would be a cosine of 4x. But since it's a 4x and not just an x, I need one more derivative of the 4x itself. So that's where 4 comes in. So you have to treat it as a squaring function to begin with. Then that u is a sine function. It's not the sine of x. You could say u equals the sine of v, right? And v is the 4x. So you're using this chain of compositions here to get to your derivative. And notice it's a product. It's one big product. So this is going to be an 8. And we'll just write it as the sine of 4x, cosine of x. And that's good enough for now. Okay, over here. Now, this one's different because you have a product as well as a composition. One of the factors in this product is the composition. It is a square root function with nested inside x squared minus 1. So that's one way to view it. So when I differentiate, I'm not only going to need the product rule, which is going to give me a 2x square root of x squared minus 1. Okay, so in other words, the derivative of the x squared times this plus now x squared. Now I need the derivative of this thing. Now you got to think of that as x squared minus 1 to the 1/2. So it is, in a sense, we'll treat it as a power function. So we're going to use the so-called general power rule here. So you'll bring down that half. You'll lower it by 1. And then you'll multiply by the derivative of that inside there. Since it's not just a plain x to the 1/2, it's x squared minus 1 to the 1/2. You have to multiply by the derivative, which is a 2x. Now it's finished. Next thing would be just to simplify a little bit. Let's see what we can do here. I'm going to write this as 2x, and I'm going to write it this way so we can see what's happening here. And this would be a plus 2 of an x cubed times the x squared minus 1 to the negative half. Okay, now that'd be good enough. And if you're working in WebAssign would accept that just the way it is. But we like to simplify more if we can, because we see a common factor here. X squared minus 1 to some power we can factor. Factor out the lowest power, negative half. And also get one of these x's out of here. So I'll take out as a common factor x squared minus 1 to the negative half. And that leaves behind a 2. And I'm going to need x squared minus 1. Okay, and over here, I still have an x squared. Okay, and now I can straighten things out a little bit. I have x. Inside here, 2x squared plus x squared is 3x squared. And I have a minus 2. Underneath, I have x squared minus 1, and that is a square root. So there's my final derivative. So the first step was just treating it as a product. I need the product rule. And first derivative here, x squared first, I did that. Then I did the derivative of this part, which required the chain rule. So I brought it down into 2x. And then these last 3 steps, 2 steps here, we'll just simplify. Okay, simplifying using some algebra.